Now we are ready to look at the force density method, nicely prepared with the previous seminars. In particular, we would like to spend all important issues and aspects of the method, such as the linear force density method, the nonlinear one, treating non-conservative issues together with self-weight and snow load, treating constraints to predict the source of nonlinearity, and alternative parametrization to deal with controlled node positions. You may find chapters on the scrub bar about all these important aspects of this seminar, just to give you the opportunity to navigate to those chapters of your interest. Let's remember, what is the goal of form finding? It seems to be simple. We like to find the shape of equilibrium of a pre-stressed cable net. Here's a little example made with stiff. We have the edge cables, we have here the cables across the surface, the edge cables which transfer the forces and the pre-stress to the vertices here at the top and here at the bottom. Eventually even we would like to find a net with minimum path length. Along our seminar dealing with the force density method, we have two alternatives to reach that goal. The first one I would like to be the indirect one. There we are prescribing force densities, Q, which are terms of the antiform configuration. Others are the pure Kirchhoff forces of second kind and the reference length. Refer to our previous seminars, and I think you remember. As a consequence of this approach, we arrive at the force density method, typically when linear equations refer to the paper by Shake. Typically, this is a very robust approach, simply because there are the linear equations, as long as we not deal with constraints and other issues in this context which make the equations nonlinear. And the result of this approach are the combination, a compromise if you like to, of the true forces S sub c, that were the Cauchy forces, and the deformed geometry. We call it here simply L, the length of the individual links. So we get both of them by this approach. The other one, approach B, I call it the direct approach. There we are prescribing directly, that's why we call it the true cable forces, S sub c, the Cauchy forces of the deformed configuration. With those given forces, we receive fully nonlinear equations in terms of the geometry, which are eventually even singular and kinematic. They are everything else but simple and easy to be solved. But if they are solved, the result is a deformed geometry. Nevertheless, no matter which approach you choose of these two, none of the cable forces arise from elastic deformations. I mean here the pure Kirchhoff forces, and I mean here the Cauchy forces, the true forces later on in equilibrium. And we have also learned that makes a little bit difference in the energy terms. We should not forget to mention that alternatively to the force density method, there exist many other techniques. But important to remember is that they all are treating the same problem, and at the end they all are solving the same equations. And the highly nonlinear and eventually singular character of the original equations is exactly the reason why there exist all these alternative approaches, such as the dynamic relaxation, further variants of the force density method, completely alternative linearization techniques, other methods which deal with the solution of singular equations, and many others. We are in principle different approaches. You see references to many people working in that field, and it's impossible on this one slide to mention all the others who also are working in these fields. But let's go back to our subject of this seminar, this workshop dealing with the force density method. And let's go now into more details to follow these ideas. Here I have a little example which helps to understand what we are talking about. It's a 4-member, 4-branch cable net. We see the surrounding box in 3 dimensions with the vertices node 1, 2, 3 and 4 and the center node where all of these 4 cables meet. So we are more or less spanning the spatial diagonals, if you like to. The cable net is also loaded by an external force. You have the center node F hat, that's the vector, with the components in X, Y, and Z direction. Then we have member 1, spanning from the center node to vertex 1, where we have the cable force S1. So you see the node and the element that just share the same number. That helps to understand. That X1 is to be understood like that. You see this calligraphic X, and that simply is a placeholder of the 3 coordinates at this node. So we have an X coordinate and the Y coordinate and the Z coordinate here for node 1. And that one is, as I said, a placeholder for all these 3 coordinates. So equivalently, we have here node 2 with the placeholder for the 3 coordinates at this node, and so on. And here the center node, again with the placeholder of the 3 coordinates of the center node. And these 3 coordinates of the center node, these are the 3 free coordinates to be determined when we go into form finding. The vertices here are the corners at the vertices of this box. They are assumed to be fixed and supported. What else we see? We see here this delta x2 as an example of the x coordinate differences of element 2. And here you see the explanation. For instance, xi, I equal to 1, 2, 3, 4. Delta xi simply means the coordinate differences between node I and node C for x, y, and z. Here you see it for node 2, delta x2, delta y2, and delta z2. Equivalently, we find that for all the other elements as well. Then we have here on the left the 3 equations of equilibrium with respect to all force components in the x, in the y, and in the z direction. Here at the center node, we can just think that pulling all the cable forces together with the external force F hat is in equilibrium. And that is expressed in these equations. So we have the member cable forces S1, S2 to S4, and we multiply that with the directional cosine just to receive by this product the x component, the y component, and the z component respectively. We do this for all 4 elements and cable links, and add additionally the external force, and if everything is in equilibrium, then we receive 0. These are the equilibrium equations, and important, they are nonlinear in terms of the coordinates, the still unknown coordinates of the center node Z. You find these coordinates in these difference expressions, the deltas, and you find it also these coordinates here in the lengths. And here you see the equation for the member lengths. It's simply the Pythagoras formula applied for the difference in coordinates. And here you see the unknown coordinates of the center nodes xz, yz, and zz. To recall, all these 3 equations are even highly nonlinear in terms of these coordinates. And alternatively, we can write these equations using force densities, because we see everywhere here just these ratios S over L for member 1, for member 2, for member 3, and member 4, and that in all of these 3 equations. And if we just replace these ratios S over L, force over length, simply by the force densities, as we have learned, they are defined, and then we can write these 3 equations just as displayed. Next is, as we just now approach to the force density method, is that we just take these force density constant. Constant, that means with respect to the form finding procedure, but nevertheless we may take a different force density for member 1, 2, 3, and 4. That's simply our choice. These are the control values by which we can just drive the procedure to find the equilibrium shape together with the forces. And then we come to these two different approaches which I have mentioned. The approach A, approach A, which just ends up in the force density method, is simply that what I just told you. We take these force densities individually different for each of the members eventually, but constant during the force form finding procedure. That's exactly is the force density method. And you see easily that these are indeed linear equations, very simple and robustly to be solved. And perhaps to refer to Hans-Jörg Schäk's paper, where you see an alternative notation of these three equations. Remember perhaps with these matrices for the force densities and the node branch matrix and all these things. But basically, these are exactly the same equations. Alternatively, approach B just stems from these nonlinear equations here at the top. But now we are taking the member forces, the Cauchy cable forces, the true forces, which we are prescribing. And there you see, if we just approach the form finding by that, we still remain with the solution of nonlinear equations, because within these lengths, they are just hidden. Still the free variables, the unknown, still unknown coordinates of center node C. And just to recall the principle of virtual work, which we have just applied, referred to the previous seminars, to understand what are the consequences and how we can consistently derive the equations, which we just have seen as a result already. We refer back to the principle of virtual work, to one of these member of these elements. We have here the undeformed length of our cable element, and we have been starting with loading this cable with the elastic load as head and the initial prescribed and constant force with these S and the sub comma, if you remember. And what remains here is that we just are looking at the goal, the shape and equilibrium. There are no elastic deformations. We directly are concentrated on the final forces. That means with the final state of equilibrium, that means we treat only with constant given initial forces like introduced in this previous seminar. And if we now follow the different two approaches, approach A, along the force density method, that means we are now picking the combination of Piola-Kirchhoff force and Green-Lagrange strain as the pair which we take to express the inner energy, which is equivalent to the negative inner work. So where we have to integrate along the undeformed geometry the product of the constantly given Piola-Kirchhoff forces of second kind, and the Green-Lagrange strain stars referring to the final state of equilibrium, if we just refer to these previous seminars. Substituting our expression for the Green-Lagrange strain, 1/2 times the difference of the length square before and after deformation. I just write this 1/2 here in front. And after integration, you see 1 L0 just disappears, and we have left the ratio force over length, which we replace by the force density as a term, an issue from the undeformed reference configuration. And that what we receive after integration, a simple formula, 1/2 times the force density, just given as an initial value from the undeformed configuration. We have the still unknown deformed length squared and the reference length squared. And very important to realize, there is a 1/2. It simply looks like the work and the energy from an elastic deformation. But as you have seen, it's not coming from the elastic deformation. It's simply just coming from the definition of the Green-Lagrange strain. It does not come from elasticity. That's important to understand. And That really means that this work expression is really dealing with a large deformation, with very large deflections, so completely geometrically nonlinear is this expression simply by the assumption that the force density, or respectively the Piola-Kirchhoff force of second kind, are chosen to be constant. And further on, we have to look into the variation, the virtual work, or the negative virtual work, the virtual energy, the internal one, we just received by applying the chain rule again, taking the derivative of the W with respect to what is free and be modified, which is definitely the undeformed length, and post-multiplying with the variation of the length. And finally, we receive this expression here. The derivative of L squared gives 2L, just cancels against this 1/2, and what remains is just Q times the deformed length, post-multiplied by the variation of this length. And from this virtual work equation, we just will derive later on all the necessary equations to solve the problem. Following approach B, the direct approach, where we just treat everything, the problem in the deformed configuration. There we pick this pair with logarithmic strains and Cauchy forces, substituting that in the work equation, now integrating over the deformed configuration, the deformed geometry, and here the work done by, now again you see the subcomma of a given pre-scribed Cauchy force now, multiplied by the related strain, the logarithmic one, with respect to the final state of equilibrium. Substituting the expression for the logarithmic strain and taking the variation. That means again applying the chain law of differentiation, post-multiplying by the virtual length here, or the variation of the length, and we just receive this expression for the internal energy, or respectively the negative virtual work. And you see we have the product of the given force in the final state. It's a given force, it's not changing through deformation. The sub comma just tells us that. And from these, we just are now developing the complete set of equations if we just look in a complete cable net. Here a complete cable net, that means you have to do that which we just display here for each individual element or cable link. For all of that, that means you have to take the sum of all elements, which just defining our cable net. So along these two approaches, A, the force density approach, and B, the complete nonlinear approach, summing up these terms here for each element. So the superscript means that we take here for element E the respective force density, the respective length, and eventually also the respective variation of the length. And here for approach B, completely nonlinear, we sum up over all elements, dealing now everything in the deformed configurations, the deformed geometry, and summing up for each element the respectively given prescribed true force as Cauchy, the subcomma just reminding us that this is really a prescribed number and the respective variation of the length. And if everything is equilibrium, it has to be summed up to 0, simply because there are no additional external terms. We are concentrating on a purely pre-stressed cable net without any extra forces or other loads. That means straightforward, the external energy or work equations or terms are 0. Something should be commented, that the variation of the length is in principle arbitrary, but they should fit together. The variation of the individual member length, this can't be taken completely independent. They have to consider what the neighbor is doing. From these formulas or these expressions, we will develop in the next step the system of linear equations, approach A, and the system of nonlinear equations, approach B, which then have to be solved numerically by typical numerical techniques. To be able to develop these equations, we have to go into the discretization of this problem and the elements. Let's just recall here with respect to our little example here. And just look at member number 1, element number 1, just spanning from the center node to the vertex node 1. Remember that the 3 unknown variables are the coordinates of node number C. And then we can just write the length of element 1 as displayed. So we have here applied the Pythagoras law with here the sum of the difference of the coordinates in x, y, and z with respect to node 1 and the z, the C, the center node. Then we have to develop the variation of that length. And that means this length can vary while we are changing any of these three coordinates. And that's what we mean by this notation here. Just if I write the derivative with respect to this calligraphic x, that means we can just replace or substitute this calligraphic x by any of the 3 coordinates. So it stands for xc, yc, or zc, just depending on what variation we would like to look at, and post-multiplying by the variation of the respective 3 coordinate. So that means we have to take the derivative of this root expression, which is just 1 over the length and 1 over 2 times the length, post-multiplied by the derivative of this radicand inside this square root here, post-multiplied by the variation of this 3 coordinate. For example, let's take for this calligraphic x, the x coordinate of the center node. Then we have to take the derivative of the length with respect to xc and post-multiplied by delta x sub c. So we have now to specifically look into the derivative of this expression with respect to the xc coordinate. Here it is. And again, just following the chain rule and the product rule of differentiation, we have 1 over 2 times the length times 2 times this bracket where we identify this xc, post-multiplied by the inner derivative of that one here with respect to xc, which is minus 1. So we have finally 2 times the bracket times the inner derivative, which is the minus here, and that is finally the derivative of the length, which we post-multiply by the variation of the x coordinate of node C, which gives us finally the variation of the length of member number 1. Here it is. Though it's not really a horrible thing to find variations with respect to the 3 coordinates. We simply have to follow this rule. And we have a little table where we just do these derivatives of the length with respect to any of the coordinates of all these nodes. I don't go into details of this table. That's one of these preliminary work which has to be done if you just go into the discretization of these equations. Nevertheless, we can now refer to these intermediate results to solve for the unknown variables, the 3 variables, which are the coordinates of the center node. That was the general equation we have developed from the principle of virtual work, just refer a few slides before. And let's now substitute what we just have prepared on the previous slide. We have to look into the variation of the lengths of the elements as, let's say, functions or the variations of the 3 variables. That means you end up in 3 equations where we look into the variation of these 3 variables and how that affects the variation of the length, the chain rule. And here you see we have prepared already on the previous slide all these derivatives of the length with respect to now the 3 coordinates, and we simply may substitute into here. That we did there, that we did in the next step. And if you look at this individual equation, you see a nice effect that the still unknown lengths of the elements, which make everything nonlinear until here, just cancel out. Wow. They cancel out, and what remains is a set of linear equations in terms here of the unknown coordinates. Still, we are free here to take anything for this variation of the coordinates. And since we are allowed to take anything, they are really arbitrary, then it is necessary that these equations are really resolving zero, that what is remaining left of these variations individually must be zero. So that must be zero, that must be zero, that as well. Then it's really arbitrary what we stick into there. In other terms, we can also take away this variation of the coordinates. And finally, that is the set of the three now linear equations in terms of the still unknown free variables, in this case of the center node. If we just expand that here for a little equation or a little example here, where we always have to consider the sum over the four elements of exactly this expression. So it ends up in these equations where we have here with respect to the coordinates of the center node, the sum of the force densities of the individual elements, and negative, the product of the force density of node 1 with x1, and again the force densities with the respective x coordinate of the related node. Here the product with the y coordinates of the related nodes, and here the product with the z coordinates of the related nodes. These are the remaining linear equations, and for this specific example you see that the first equation is only a function of xc, the second only a function of yc, and that one only of zc. That means we can, in this little example, individually solve each equation for the respective coordinate of the center node. I show you that with some data. We start here with the four elements, giving individual force densities for these elements. I simply pick some numbers, 2, 3, 2, 1. You can easily take something else. Then we have a second table referring to the nodes, node 1 to 4, where we have the coordinates of these nodes. These are simply the coordinates of these vertices. Then we have to take these products, the q times the x. That's why I just also transfer these q's here in this table. Then we can easily see what we have to do. So for element 1, q times x gives 0 again, q times x again 0, q times x gives 4, 1 for the q times minus 3 gives minus 3. Pretty easy and simple, straightforward. We do that also for the products of q times y and q times z. Then to receive xc, what do we have to do? We have to take the sum of the q times x's and divide it by the sum of the q's. That's the next what we do here. That we sum up these columns here. That gives 8, that gives 1, 5, and 20. And that we can use to determine the coordinates for the node C, which is 1 over 8, 5 over 8, and 20 over 8. And that is already the result for the form finding of this specific example. Then we transfer this intermediate results with respect to the geometry back to the elements, and we can now determine the lengths simply by Pythagoras between the coordinates of the two nodes and the coordinates of the center node. That gives the individual lengths of the element in the state of equilibrium, and then it's straightforward to determine the member forces in the deformed state of equilibrium simply by multiplying the deformed length by the force density, where we just have taken those at the initial given values and just multiplying that, and that is finally the result. Done. Very simple at the very end and straightforward and completely convincing by the robustness of this approach. Here I just show you how we can do that with Excel. That's exactly these tables I have shown you on the previous slide for the elements and for the nodes. And here's a little screenshot of applying this Excel sheet just to show you how convincingly the technique works. Yeah, we see here a first state of equilibrium for this data for each of the 4 elements we just have chosen the first density equal to 1. And these are the coordinates of these vertices just at the vertices of the surrounding box. Let's just modify the first density for member number 2. Let's take 2. And as a consequence, you see the pre-stress force now becomes larger here for the second element and just pulls the center node towards this element, let's say. If we just refer to the forces in the geometry of equilibrium, you see, these are the results after form finding, and it's hard to understand or just see the relation to the force densities. That's one of these dangerous parts of the force density method, that people may mix up the force density with the pre-stress forces. That gives a trend that a small force density refers to a small pre-stress force and a large one to a large one, but it's impossible to really guess about what are the final forces if you just look at the force densities. As I said, and as we know now, the force densities are living are terms of the antiform geometry, and that of course these are the true forces, the Cauchy forces, which live in the deformed geometry. Let's take 3 here for member number 3, and you see member number 3 is now also pulling, and this is the largest force density that is reflected also here in the forces in equilibrium. We just may walk around here a little bit if you like. The figure is jumping because of the change in scale. Let's look more from the side. And let's pull a little bit more for element number 4. Let's take a really large value. Wow, so that's how it's pulled in that direction. We can walk even more around. Sorry that the graph is scaling and hopping, but I think you are able to understand what's going on. There we are. Yeah. Well, try it by yourself. It's really fun and not an issue at all, to set up tables like that to solve the form finding problem. Finally, we can come back here to this previous slide. We just have identified the 2 approaches A and B. And a little comment for approach B, where we just start prescribing the forces into deformed configurations, the true Cauchy forces. We have a nonlinear equation, and that is really a problematic issue, because it appears that for many cases these equations are problematic. We call it singular. That means they have a kinematic problem, and they can't be solved without any extra issues. And that, as I said, it's a reason that there exist so many different techniques solving form finding problems. One approach which we apply here in this context is that we just repeatedly solve along approach A, the linear force density method, repeatedly apply this approach, where with each iteration step we modify the force densities, which again are assumed to be constant for the next linear step with the linear force density method. We show that in a second. That will be the updated reference strategy, with a certain reason why we call it like that. So we are able to replace the original approach B by repeatedly applying approach A, and also by that able to solve problems with prescribed forces for the unknown state of equilibrium. Here we have a little screenshot from applying STIF 3D for our linear force density problem. We just start with the initial geometry, as you see from the top, from the side, and here in a perspective view. And after one step, we have reached the state of equilibrium, You see the residuum is 0. That means all equations are solved for 0. Everything is fine. And in some sense, that we only use one iteration step seems to be disappointing for many other people who say, oh, I don't see anything, it's so not dramatic at all. I like to see how this geometry is nicely moving into the final state. That's true. Force density method is highly effective and efficient, and it might be disappointing if we don't see the evolution of the optimal geometry. We, the developers of the method, wow, we are completely flashed. We are able to reach the optimal solution with one step. There can't be anything better than that. Let's finish this chapter by applying the force density method to a simplified model of a very famous structure, the Tanzbrunnen by Frei Otto in Cologne. And if we just take a look at the perspective of the initial geometry, the undeformed geometry, you see that we have 4 low points, 4 supports, and we have 4 high points, which we simplify model also as supports instead of having posts below. And there you see that we have only 4 low points and 4 high points instead of the 6 of the original structure. Looking from above, you recognize the outer edge cable, the inner edge cable, and here's the supporting cables. And if we look closer, we maximize this view. We can also take a look at further aspects of the modeling, in particular the force densities. Let's reduce the scaling of the nodes that we get better access to the cable elements. Let's start with this one here, this element from the outer edge cable. If we edit it, you see we just have taken the force density to 5, quite obviously. Let's select an element of the inner edge cable. Here it is highlighted. You see we have a force density of 20. And if you take a look at one of the surface cables, let's take this one here, you see that we model these with the force density 1. Let's also look at a circumferential surface cable. You see as well, the cable net is modeled by a force density of 1. The supporting cables, for instance this one here, if you edit it, we see is also a force density of 5 applied. So that how the mesh is modeled in terms of force densities. Let's make the nodes larger again, so that makes sense, and minimize that view. And then we are ready now to start the force density method. Look at the options, the operational options, the accuracy. We allow maximum 40 iterations, which is not necessary because for a linear problem we expect not more than 1 iteration, and we just start with the original data. Okay, and let's do the analysis. And indeed, we are finished after 1 iteration with a residuum of 10 to the minus 14, which is a numerical 0. Let's maximize the perspective view and let's walk around a little bit. And that's the impression of the form-found structure in equilibrium. We can take a look at the forces. For instance, let's look at the force in the edge cable. For that we highlight here this menu here for element 45. We don't see too much because we have to adjust the projection. Let's just take a look from above and let's just look at the force. You see we have now a force of 26.73. Checking the force densities, we just select force density, and indeed you see for this element we had the force density of 5. What about this supporting cable? We have also started with force density 5, and we see the force now is 65.18. We can also take a look at the final length. Here selecting the length, and you see the final length of this cable here is 13.04, Or if you just take a look here at this piece of the edge cable, we have a length of 5, quite obviously. Checking the force density, indeed it's 5 as it just have started, and looking for the force, we are now here at 25. Well, let's go back to the curation mode and minimize the view. And let's just modify the force density here for the supporting cables, making sure that we only pick them. Now come on. These are the them, there we are. Let's edit them. Let's increase the force density, let's say to 10. And let's do again the analysis, deselecting everything, the analysis. And taking a closer view here, you'll realize that we have increased the curvature in the surface by pulling with a larger force here towards the support. Again, taking a look at the force, we are now with 87. It was 65 something before. Checking the force density, yes, indeed it's 10 now, and the length has been reduced to 8.7. Yeah, that's it. Try yourself some other examples. We now arrive at first nonlinear aspects, which appear, for instance, if we follow this direct approach, I call it number B, when we directly prescribe the true cable forces of the deformed configuration and try to find the related shape of equilibrium. In particular, that is a question of minimum path length nets. These are nets where everywhere we have the same cable force. These kind of problems, however, are problematic. It appears that the equation systems are singular or kinematic, and we can solve this problem by applying the updated reference strategy. Let's first of all study this little example. It's a plain cable net with 3 cables supported as displayed, where the top nodes are distance 2 times A, and the overall height is also given by H. What we like to determine is the shape and equilibrium with these 2 free variables X and Z. And what we like to do is that we directly try to prescribe the forces, the cable forces in the deformed configuration, and we call that a weighted minimal path length if these forces are not equal the same. Some we may have different values, and we call it a minimum path length net if all these forces are have the same value. In this case, the sum of the individual lengths of these 3 cables just appear to be the minimal possible value of this sum for every other choice of X and Z. We apply this problem, this functional, where we just minimize the internal energy, and the variation of that appears like that. Just refer to the previous slide, from which we just derive these 2 equations with respect to the variation of the individual lengths of these cables with respect to these 2 coordinates, 2 free coordinates. Just refer to the previous slides and you will see what we do in detail. In particular, I repeat these, you have to look at this individual element lengths for these 3 elements as displayed, and we have to look for the derivative of the lengths with respect to these 2 free variables, and that is the result as a function of the horizontal width of the problem and the overall height of the problem. Substituting here in this short expression, you see that we just have to sum up over the 3 elements for X and Y coordinate, and the 3 cable forces just pop out. As you see immediately, that is a set of nonlinear equations which can only be solved iteratively, for instance with the Newton-Raphson iteration. And the solution, straightforward, without any problem, is what we see here. X appears to be A. We can see that immediately because of symmetry. and z, the vertical coordinate, appears to be a over the square root of 3, and that we receive if the three prescribed forces are the same. The value is not of importance, no matter how large these forces are. We always receive the same geometry, simply a scaling of the forces where the geometry remains the same. And that is the iteration history if we solve that with stiff. And in particular, just take a look here at the residuum. After the first iteration, you see we have the exponent to be -1, and it seems that we already are close to the solution. And if you further look at this exponent here, so next iteration we have 10 to the -2, and then we have 10 to the -4 and 10 to the -9. And that's exactly what we call a quadratic rate of convergence, that these negative exponents just scale by the factor of 2 from 1 to the next iteration. So we have -1 times 2 is -2, -2 times 2 is -4, and again -4 times 2 is -9. Yeah, so we are even better a little bit than an exact quadratic rate of convergence. That is quite important, this finding, because that's the optimal, the best rate of convergence any numerical algorithm can just achieve. And indeed, the Newton-Raphson technology or method has this property that it converges quadratically, of course, if everything is programmed right and the model is set up right and so on. So it's also a check if your method is converging quadratically, that presumably your code is programmed correctly. It's also well known that if three cable forces just meet at a common node and all of these forces are of the same value in tension, then these bars meet by 120 degrees, which is also correct here. Next, we change our problem, and instead of directly controlling the cable forces, we now directly control the force density. That means we are indirectly controlling the member forces and the length. Following this idea, as before, the force density method, we arrive at these two equations, which further on just appear, of course, to be linear in terms of x and z, the two unknown free variables. And if we solve that, we just receive these results for x and z, again as functions of the width and the height of our structure, but also as a function of the given force densities. And there you see, by applying stiff, what you will receive by the force density method, just depending on your choice of the force densities. And it's clear that it depends on this choice how close you may get to the minimal path length solution. And exactly that is the idea of the updated reference strategy, that we repeatedly solve the linear force density method with chosen force densities just by iteratively adapting the force densities that at the very end we just appear at the optimal minimal path length with this 100-degree angle between those cables. Yeah, let's just study how that may work. That is the data we just apply here. For little a, we just take 2. That means the overall width is 2 times a equal to 4. The overall height should be 6. And the optimal, let's say the forces in the deformed state, we try to converge to the number 2. We start with the initial solution, iteration number 0, with initial data for z. To make it simpler, we keep x equal to a, so we have only one free variable, so that this table is not overloaded. So we start with z equal to 0.1. With this choice, we have the length is L1 equal to L2 because of symmetry, or approximately 2, and L3 is just 5.9. The member forces, of course, are given. There should be 2. And by that we can determine the force densities in the two members 1 and 3 simply by dividing the given force by the actual length as a function of the actual z coordinate. Then we receive these two numbers for Q1 and Q3. So now we start the force density method with these force densities, substituting this data into these two equations. Yeah, now we have the force densities given. Q1 is equal to Q2. Yeah, A and H are also given. And with this data, we are now at Z equal to 0.87, from which we can determine the length L1 and L3 after this first step with force density. Multiplying this actual length with the given force densities, we receive the forces as output of this force density step. We can also determine the angle between those elements, and you see we have now 174 instead of 120. And if we look at the sum of the weighted lengths, that means the sum of the length times S, that's exactly the weighted length, we receive just the value 19.8 as a reference for the next iterations. Then we start the next iteration number 1, simply by transferring the result of the iteration step 0 to iteration step 1. You see, we just transfer this data. And then with the goal forces, which of course remain the same to be 2, we can determine with this modified lengths, modified force densities, Q1 and Q3, by which we can now start a next linear force density iteration. Then we can determine the new geometry in terms of Z. Here's the new value. We can determine the new lengths of the cable elements. Here is the data. And we can determine as output the cable forces by the product of the lengths with the force densities of iteration step 1. And you see we just receive this data, and you see it just starts to converge to 2. At the very end, these two should converge to the values we prescribe, which are 2. The angle is also modified. Now we are at 133 approximately, getting closer to 120. And you see the weighted length is also reducing. Okay, next we again are transferring the found geometry to the next iteration step 2. You see we transfer Z, L1 and L3 to here. Now again applying here are the goal forces to determine the force densities for the next step. 2 divided by this, and by that we receive these two values for Q1 and Q3. And again, we can start one linear iteration step in force density along the force density method. That are the results in terms of Z, L1 and L3, from which we can determine the new values of the forces by again multiplying these lengths with these actually modified force densities. And again, you see it nicely starts to converge towards 2 quite obviously, and also the angle is just converging towards 220, and the length is also reducing. And that we repeat as much as we like to until the data is converging. You see it here, it starts to converge to 2 here, and also the angle is just converging to 220. And you see the length is also reducing until here it's not possible to measure it anymore with only 5 digits. And it just, it's a question of taste when you just stop this iteration. But by that, we are able to really solve this minimal mesh problem. Why the minimal path length problem is problematic, I'll show you on the next slides. Here, everything is okay. That is not a problem, simply because, so you see it with the elements, with the structure is quite obviously not kinematic. There's no problem that is possible to converge. And this problem with the kinematic systems, singular equations, we can nicely study with this little basic two-dimensional example where we just try to find the path of minimum length between the left and the right support. And we do that with a pre-stressed cable. without mass. And it's clear what is the solution. That's exactly this one here. If we pre-stress this cable and there's no self-weight, then we receive this ideal straight line. And let's now model that. And we have the data. The distance should be capital L. And we model it with two elements, as we did that before. We have link number 1, link number 2, and the node in between, which we call K, and the two free variables, that's the horizontal coordinate X and the vertical coordinate Z. Then we introduce the coordinate differences. Remember one of the previous slides that we did that. So for member number 1, the delta X, the difference of the coordinates of member number 1 is just the coordinate X itself. It's just the difference between the left support and the position of node K. And the delta X for the second member is simply the overall length of our problem capital L, the distance between the supports, minus the X coordinate, that is delta X2. And the delta Z, that's what both elements just share. That's just the Z coordinate itself. The distance between the top node and here this node K, that will be the delta Z. Then we can determine the individual lengths again by Pythagoras as displayed. What we just receive these lengths again as functions of the two free variables X and Z. And then we are able to set up the two equations of equilibrium in the horizontal and in the vertical direction, where for the horizontal direction, where the two horizontal components of these two forces should add up to 0. And the horizontal component is determined by the force times the direction cosine delta X over L, and that for element 1 and element 2. And the vertical components are just determined by the force multiplied by, again, the directional cosine, the delta Z over the respective L. The signs I just have adapted to the sign convention in this graph. Next, we see that the delta Z1 and the delta Z2 are identical to BZ. We just plug that into here. And then we just say, okay, we apply the same force for both elements. S1 is equal to S2 equal to S. We just take away the indices. And that finally are the two equations which we have to solve. We can start with the second equation. And there you see that the S is positive in tension. The lengths are positive. So we have here a positive number and here a positive number. And if we both these numbers just multiply by the same value delta Z, then the sum can only be 0 if the delta Z is 0. That means we have immediately found the optimal geometry, which is the straight line. But there are severe consequences with this intermediate solution. Taking delta Z and plugging that into these equations for the lengths, then we receive L1 and L2 equal to be the coordinate differences of the first and the second element. So we see it here in the graph quite obviously. The delta X1 is equal to X and the delta X2 is equal to L minus X, which is the length of the second element. If we substitute this intermediate solution into the first equation, into here, then you see that we just divide delta x1 by L1, which is 1, because delta x1 is L1. And also here, the length just cancels out, and we receive from the first equation S minus S, which is 0. That is uniquely true for every choice of x. And that exactly is the problem. We have a singular set of equations where we can use only one equation, that one here, the second, to determine Z. But the first equation is completely useless. It's uniquely true, this equation, for any choice of x. We are not able to determine the position of this node in x direction. We call this a floating node, simply because if we just consider several positions, you can really see this node flowing around, and it's always true. The geometry is not changing. And that exactly is the case for many problems of minimal path problems that the nodes are floating or like to float on the surface. And for cable nets it's even more problematic because we have three equations in space. Only one equation makes sense, which is normal to the surface, and the other two equations, which treat the tangential movement or the tangential positions of the node, are useless, and the node can really freely float tangentially on the surface. You need some good ideas to attack these kind of problems, and our approach is the updated reference strategy and adapt the force densities iteratively as you have seen before. If you just follow our continuum mechanic approaches, don't go into details, just refer to the previous slides how we do that. We just receive the same result as for these straightforward approaches, that the equation for the z coordinate exactly gives the result that the z should be 0. And with z equal to 0, the other equation just is also useless. For any value for x, we can check it. Let's now solve this problem applying the force density method. Again, we have these two equations in horizontal and vertical direction. You are expert now. In the meantime, we observe here this ratio S over L and can replace that by the force density. And then we have linear equations in X and Z, where we just have to choose the force densities instead of the forces, the force densities. Substituting for the coordinate differences, the values we have identified before, we just receive these two equations in X and Z, which we can solve. Again, we see with positive numbers for Q1 and Q2, we receive immediately Z equal to 0. And from the first equation, we receive this result for the horizontal coordinate as a function of the force densities. And that exactly is the nice property of the force density method again, that even for this kind of problems where this node wants to float away, we receive a unique solution, of course, as a function of the given force densities, which you may take as you like. Let's just check exemplary numbers for the force densities. If we take Q1 equal to Q2, both the same value, then we receive a symmetric solution where x is 1/2 of the overall length, where the two individual lengths are just the 1/2 of the overall length. From that we can receive the member forces, multiplying the lengths in equilibrium by the force densities. And from symmetry, of course, the two forces are the same, 1/2 times L times Q2. Let's now take for Q1 the half of Q2, and if we substitute that into this equation, we directly, of course, receive a solution which is x 2/3 of the overall distance with the two individual lengths as displayed. See, with a larger Q2, larger than Q1, then the member 2 pulls more, let's say, in terms of the force density, and it moves to the right. Nevertheless, although the force densities are not equal, as you see, the forces should be equal, because from equilibrium we see the force should be the same throughout the complete structure. Let's check if that is really the case. S1 we receive by multiplying Q1 and L1, where we have 2/3 of the overall length times 1/2 of Q2, which is 1/3 of the overall length times Q2. And that's exactly what we receive as well if we determine S2 by the product of small letter L2 times Q2. So it's indeed true, and that might be surprising at the first glance, that for non-equal force densities we receive equal forces, which must be the case, otherwise it would not be in equilibrium. And the other way around, if we take Q2 just half of Q1, the position would be just more the left side, whereas the Q1 is larger than the Q2. It will be at the 1/3 of the overall distance, with the smaller L1 and the larger L2, just as displayed. And again, if we just check the forces by the product of the individual lengths times the individual force densities, they again appear to be the same as just 1/3 of the overall distance here times Q1. Yeah, we have a unique solution for X. Yeah, if we apply the force density method and the tangential mesh distortion is prevented. Yeah, no problem anymore with floating meshes. That's a good message. Let's now study our basic 2D example with stiff. You recognize the problem. To the left, to the right, there are the supports. In between is the structure consisting of our two elements. Let's check the data. Yeah, here for element 1, we just have selected here 2 as the goal, pre-stress. For the NLN, the nonlinear option. The force density is not of importance, this number here. Let's go to element 2, and again here's our selected goal stress, pre-stress force, which is supposed to be 2. Okay, deselect this element. Let's check the algorithmic options here. We allow not more than 20 iterations. Everything else is on the default values. Okay, and now we're ready to start the solution. Let's go. Oh, no convergence at all. The problem completely explodes. And the reason is the singular system of equations. Let's see what we can do to make it a little bit better. There you see this value maximal step length. I give 1. So that is the maximum step size within one iteration which is allowed. Step size measured in terms of the dimensions of our problem. Let's say 1 meter, something like this. Okay, let's try again. We go to the starting, to the initial geometry and start our analysis. Yeah, and at least it just converges to this horizontal geometry as intended. Yeah, and let's go on with the analysis. And as you may see, there's no conversion to be observed, and you clearly see what I showed you here in the PowerPoint slides. Yeah, this ever floating of this node horizontally. There's no solution possible. Indeed, the reason is what I have explained to you. Let's go back. Let's just try the IASS option. Here the options for the theory. We go to IASS, and I don't take back the maximum step length. It's perhaps not necessary, and we start really from scratch. We reset all data. So, okay, let's go on. Pop. Yeah, there we are. And you see our technique with IASS is just stabilizing the problem such that we are adapting step by step the force densities and reach the goal. Let's check if it's really okay. Let's look at the normal force here, and for element 1 as well as for element 2. Wow, it's exactly reached what we like to have. A minimal path net with given goal forces. Let's now apply plane force density, just to study what happens in that case. Let's switch to force density. We have still activated the IASS option. Let's go to the force density option. Everything else is on default. It's okay. Let's check the force densities. Member number 1, we have force density 1. The value for the pre-stress force is not of importance. If we go to plane force density, element 2, also we start with force density 1, and again the value for the pre-stress force is not of importance. That is okay. And now we are ready to start the analysis, and as to be expected, one iteration step, and we reach the deformed configuration, the deformed geometry in equilibrium. Let's take a look at the forces, and you see that we have for the element 1 the force 6, and for element 2 the force 6 as well. Something what has to be expected, refer to our presentation. And also you see the length is 6. Let's go to length here. Length is 6, and multiplied by the force density, which is still of course not modified. It's 1, and everything fits together. Force density 1 times L6 gives of course the force 6. Okay, Let's modify our problem and let's take a larger value for the element 2. Let's take perhaps here the force density 2, why not? Now it's just twice as large than the force density of element 1, which still is 1. And if we do the analysis, as to be expected, the length of element 2 becomes smaller there where the force density is larger. The force density is pulling the position of the center node towards itself. And if we just look at the forces, however, we should receive the same forces. Element 1, we have force 8, and element 2 as well. And that fits also for the formula. You see the length now of element 2 is 4. And the force density is 2. 2 times 4 is 8. That fits. And if you go to element 1, the force density is 1, as you see. And if you look at the length, it is 8. And multiplied, is 8 also for the force. That works. Let's now just flip it over. Just take 2 for element 1. For the force density and 1 for the force density of element 2, and we just receive the opposite or just the related result with a smaller length where the force density is larger and a larger length where the force density is smaller. And again checking the force should in this case as well 8. As we see immediately, the length must be 4. If we just count here the distances, the grid points, the length is 4, the force density is 2, we have to get 8 for the force, and vice versa for element 2. But always important to realize, the linear force density method is just converging in exactly one iteration. The residuum has reached the numerical 0. Finally, let's take a look at this problem at the larger middle path network. And you see it displayed with supports and the net, the cable net in between. As you may remember, a minimal path network is equivalent to a pre-stressed cable net with the same forces in the deformed equilibrium. And if all the forces are the same, the node with 3 branches, then the angles between 2 of these branches should be 120 degrees. By that we can check whether everything is right, at least visually. Let's take a look at the data. All of the elements, there we give the goal force, pre-stress force as 2. In this case the force density is not of importance, this number. And if we just look at all the other elements, 2, 3, 4, 5, 6 and 7, indeed all of these elements have the same prescribed value, which is supposed to be 2 at the end of the iteration. Let's take a look at the algorithmic options, the accuracy, where the iterations should stop, maximum allowed iterations, and everything else is on default. Then we are ready to start the analysis, and here it is. Oh Jesus, it seems not to converge. The reason is that because of the high linearity, it may overshoot the solution technique. We can damp that a little bit by just pre-scraping the maximal step length within one iteration. Refer to the previous example that we did that also to really a little bit damping the Newton-Raphson method, and we are ready to start again. And you see it nicely converges to the final state in equilibrium. And I do it again. If you just look here at the residuum, you may see that it's really converging with quadratic rate of convergence at the very last step, at the last steps of iteration. And you see we have to take control only 2 times by 6 iterations, just to damp the method a little bit in the beginning. And as it is consolidated after the first 2 iterations, you see that it is nicely converging as it should. Let's check if we really have reached the goal with respect to the element forces. Here the forces, element 1, we have 2, element 2, 2, and so on, 7, all of these elements have reached the final goal as it should be to be 2. Wonderful. Let's now modify the problem a little bit, and I just divide this element into 2 parts. Yeah, I just replace this one element just by 2 elements, and if everything is under pre-stress intention, of course it should not change the result at all, but let's see what our algorithm thinks about that. We do it again. Yeah, and you see it does not converge after 30 steps, even if you just go on with analysis. You see, again we have the problem that these 3 nodes here along this element cannot really find the solution, because this node in between is starting to float and completely corrupts the analysis. Here again we have the problem of a floating node along this direction. And what is the recipe against? Yeah, the recipe against is take the IASS option, start from scratch. We can also take the maximum step length for stabilization, for damping, and just start again. And nicely you see it's converging again to the final solution, where these 3 nodes here are really on one straight line here, and the center node is not floating anymore. Let's check the forces, and you see again we just have reached the goal. Yeah, there's something I did not mention yet, but it's quite obvious. For the price with IASS that we reach the goal, we'd have much more iterations with respect to the accuracy which we have given. Even 30 steps are not enough. If we just go further, do some more analyses. Finally, it finishes within the accuracy which we just tried to achieve. This type of convergence, quite obviously, is not quadratic anymore. It's a linear rate of convergence, and that is the price of IASS, that we reach the goal but pay with more iterations. But it's even better than receive nothing. Let's finally discuss some extraordinary cases when we try to find minimal path net. You see, we have here a spatial cable net with 2 high nodes and 2 low nodes, and we have here this rectangular grid of elements. And if you just take a look at one of these elements, for instance, this edge cable here, you see that we have the pre-stress force which we would like to reach of 2.5, and that is the case everywhere at all the edge cables, but also in the interior, in the inner elements. There we have also the same goal force what we would like to reach. We directly start with IASS, because if you just look at the internal node here, it's quite obvious that this node may float on the surface horizontally and vertically here. So the only stable direction would be that one, in that direction. So it's one of these cases where stabilization techniques like that IASS must be taken anyway. What about the algorithmic options? Everything is set on default, and we have 30 iteration steps allowed. The IASS option is taken. Let's start it and observe what happens. Whoa! It just shrinks to, let's say, 2 cables in the diagonal. And indeed, that indicates there's no solution possible other than what we see now, where the forces in the elements are everywhere the same. Let's check where we have what we have reached after 30 steps. Let's click this one. No? Yeah, we are close. It's not so bad. But obviously, the surface has disappeared. Other solution is not possible. So, how to modify the problem? Obviously, we have to give larger pre-stress forces to the edge cables. Let's try to do this. I select the edge cables here, the elements of the edge cables. Here we are, and give those edge cables another pre-stress force. Let's give them 12.5. Well, then let's start again. And you see it's converging, but if we go further iteration steps, you see we have another situation similar to what we had before. The surface cables just shrink again to just 2 cables parallel to the outer edges, but disappear to be just 1. Let's just take a look at the forces. Here the edge cable, yeah, we are close to 12.5, and the interior, yeah, around 2.5, but not exactly, yeah, not exactly, and they may vary, yeah, and that's exactly the case. What can happen if it's impossible to really find an equally or nicely distributed cable net if we try to find the minimal path. What is the consequence of that? The conclusion? The conclusion is that these kind of problems we can only attack with additional constraints. So for instance, controlling the lengths of the cables, in particular at the edges. Again, for a price, and the price would be that we just get clear to our goal forces, but will never reach them according to the constraints which force the solution to deviate from our ideal. That's we have to be aware of, and with the knowledge about that, we may find nice compromises which make sense from architectural or engineering point of view. We get now to the subject of constraints. In particular, let's concentrate on length constraints first of all. And I've mentioned several times already before that as soon as we just treat constraints, the force density method becomes automatically nonlinear. There's no way out. Constraints always will turn the method into a nonlinear method. First example, let's go back to our 3D cable net we have been discussed before on the lines of minimal path length. And if we may modify the problem, for instance, like that, we just prescribe the length here of the links of the edge cables, here 2.7 and here 2.9, just an example, then we of course are just modifying the final shape of the structure. Or in this case, we just constrain the length of the interior links to 2.0. That are questions of practical interest, because we would like to build structures of equal-sized links, and that of course makes sense from an aesthetic point of view or from a kind of production point of view. Or here in this case, we are constraining the length of the post. If we just put posts here at the high points of this cable net, and we have just 2 solutions, to the left with a prescribed length of 6 and here on the right with a prescribed length of 8. Think of any dimensions you just prefer. Now, how are the equations being modified? Here the original form finding equations along the force density method, the overall internal energy, the sum over all elements, and the element-wise energy and internal energy, which has to be minimized at the optimal solution. Therefore, we have to look into the first variation, and that leads at the final end to the linear equations in terms of the coordinates of our problem. Then, additionally, we have now to consider the length constraints. To believe they are also formulated element-wise. And if LE hat is the prescribed length of element E, then at the optimal solution, of course, the actual length has to be the prescribed one. That we transfer into a constraint equation, where we look at the difference of these two, the actual length and the prescribed one, and at the optimal solution, quite obviously, this difference has to be 0. We can also write this constraint in a quadratic variant, where we just look at the difference of this length, this square, the actual one, and the prescribed one, and quite obviously at the optimal solution. Also, the difference of the square lengths is 0. For other reasons, we just multiply that by 1/2, which will not change the expression. Then We extend the form finding equation. That means we add element-wise to the energy term, this term, which is the product of the constraint, times what we call the Lagrange multiplier. And finally, we sum that up over all elements, where eventually an element also may have been a constraint of the length. And rather than minimizing the energy as on the left-hand side, we will now just look into the stationary solution of this Lagrange function. That means we have to take the overall variation, the variation with respect to length, and the variation with respect to the Lagrange multiplier. And that has to be in total 0. And that divides into two parts: the derivative with respect to the geometry, last not least the derivative with respect to the coordinates, which this derivative has to be 0 at the very end, and the second part here, the derivatives with respect to the Lagrangian multipliers by the formulation here. Here you see by this definition, taking derivative with respect to the lambda, we receive just back the constraint. So you have two sets of equation which have to be solved for each free variable x, refer to the leading chapters, and at the second set we will just have the additional equation as the derivative with respect to the Lagrangian parameters, which also has to be 0. If we look at other constraints, we will see that later, we treat them equivalently. Let's now focus on this alternative formulation of the constraint, which I call the quadratic variant, where we just have here the difference of these lengths squared. And if we now look at the contribution of the element to the Lagrange function of the problem, then we have here the energy term and here the constraint term together with the Lagrange multiplier. Now substituting the constraint equation into here, we arrive at that. And you see immediately that for the energy term and for the constraint term, we have these brackets which look pretty much similar. The actual length squared appears. The reference length is squared here and the prescribed length there. And we have this 1/2 here, the leading 1/2. If we take the variation of this expression, the constant terms, the L0 and the L hat, just disappear, and what remains is that means you have the same derivative here as there of the element length squared. Take the derivative, we have 2 times the length, which just cancelled out against this 1/2, and we can rewrite that like here, this variation. There you see immediately that the Lagrange multiplier just adds up to the force density, which means they are equivalent, the Lagrange multipliers to the force density. So that leads to the first idea that dealing with these constraints, we can do that by modifying the force density expressions. And that's exactly what you may find in the paper by Hans-Jörg Scheck. We will have just taken a look in the introduction. And we will come back to this later as well. Nevertheless, it appears if we do it like this, in comparison with the linear variant, we would just look instead of the difference of the length is squared at the difference of the length is, it appears that this quadratic variant is numerically less robust than the linear one. That's simply a finding from experience, and we may explain it like that. First of all, we should completely precise what we mean by the linear variant. That's what we call the linear one, where we just look at the difference of the length instead of the quadratic one, where we look into the square of the length. However, we should not forget that the length itself is non-linear in terms of our free variables. So what I call the linear variant of the constraint is also a non-linear one, but it's less non-linear than the quadratic variant if we just look at that graph. So it's a really a vague kind of explanation, but it explains the problem. So the quadratic variant in terms of the length is looking something like that here. The linear variant in terms of the length, but non-linear in terms of the coordinates. Yeah, you see we plotted against a coordinate. Is also, of course, non-linear. Yeah, this is a non-linear function. But if we look here at the root of these two formulations where these constraints are 0, you see that the blue line seems or appears to be more linear than the red one referring to the quadratic. That's what I mean by less non-linear if we just look in these two variants. And that's what the numerical experience tells us, that in quotes the linear variant of the constraint behaves more robust than the quadratic one. We have no overshooting, as we just have seen in one of the previous examples. At the very end it converges faster. Finally, it appears that the force density equations with constraints are nonlinear in terms of the free variables, and of course they must be solved iteratively. Looking more in detail, you see here the element contribution to the Lagrange function, the energy term still linear along the force density method referred to the previous chapters, and here the chain rule applied to the derivatives of the constraints, derivative with respect to the length, and post multiplied by the derivative of the length with respect to the free variable, and referred to above here. Yes, indeed, that at least is a nonlinear relation. The second part of the extended set of equation stems from the derivatives of the Lagrange function with respect to the Lagrange multiplier, where we just receive back the constraint, and again the constraint, look above, nonlinear functions in terms of the free variables. As a convincing example where we can apply length constraints on cable elements, let's consider this example which we have done already before, about this three-dimensional minimal path cable net, and where we just observed that there don't exist really solutions, and because of that cables just fall together. And to avoid that, quite obviously it makes sense to apply length constraints, for instance here on the elements of the edge cables. Let's try to do that. Let's go back to creation mode. Let's select the elements of the external cables, and let's just apply additional constraints on the length. Let's go to loads and activate the length constraint, and let's give some reasonable goal length. So 2.5, that's exactly the length of the undeformed grid here. It does not make sense, of course. You have to make it a little bit larger. Let's take 2.8. Deselect the element. Okay, let's look at the algorithm parameters. Everything is okay. We take 50 iterations and start it. And there it is. You see nicely as it seems to converge. After 50 steps, not completely converged, but if we can go further, nothing happens anymore really. It really now had converged. And let's check now the lengths of the cables at the edge, and you see indeed we have reached the goal. All of these member lengths are exactly the prescribed value of 2.8. That is convincing, isn't it? And if we constrain the lengths of these inner cables, not these, additionally to the goal length of 2, deselecting, then we just receive this result, which looks perhaps even more harmonic with the controlled lengths of the edge cables and this interior one. If we just look at the 3D appearance, I think we can accept it. And if you check the forces of the cables, then you see that the unconstrained elements, of course, have reached the goal forces of our procedure, while all the constrained elements deviate from the goals. At the edge we had 12.5. You see these are considerably deviated from this value due to the constraints, and the constraint in inner elements, they're supposed also to be at 2.5, that's the goal value, also of course deviate considerably from these goal forces because of the constraints. That is consequently. Finally, let's come back to our transpolant example. Let's put some posts below the high points. You see it here if we just walk around in the perspective view. And you see it also here from the side view and here as well. Let's edit one of these posts. We can see what we did. So we have activated the length constraint and we just give a goal length of 12. Deactivate everything. And let's just check the algorithmic parameters. And you see everything is on default. And we have maximum of 40 iterations, which you will not need. Okay, let's start the analysis. You see it's nicely converging. Also again with quadratic convergence. And let's now check the length of the posts before we just maximize here the perspective view. So we can nicely walk around and explore the found geometry. Perhaps we could make the example a little better with just strengthening the pre-stress force here in those cables. But nevertheless, let's check here the post for its length. And indeed we have 12. And that one as well, and that one as well. And if you like, we can also just check that one here in the back. Yeah, it worked nicely, our length constraint, and that is our final example for this chapter. Thank you. We now come to self-weight and snow load. Snow can be considered with respect to the projected length of the cable, and we will see just in a moment that these two load conditions generate non-conservative mechanical problems, which in particular will lead to non-symmetric stiffness matrices. Let's just look at the weight of a certain element, E, which just runs from the generic number 1 to the generic number 2 with the respective coordinates at these nodes and the vertical deflection component 1, W1 at node 1 and W2 at node 2. We consider now the external work of the specific element in terms of the specific weight, which acts in direction Z and performs work with this vertical deflection coordinates and components W. We treat the self-weight of a cable element, if we would like to consider the surface weight, for instance, of the cladding, then we would treat that equivalently to what we show here. But now we are concentrating on the cable only. Yeah, that is the contribution of an element E to the external work. It's the integral or the actual length by the specific weight, which performs work with the vertical downward deflection W. We integrate along the longitudinal coordinate of this element, which here we call S. Look at that. Note that. It's very important that we realize that in form finding the elements become longer or shorter. We have a change in length, which is not an elastic modification. That means by a change of length, the element becomes heavier or lighter. And there's an important difference to elastic deformations, where by elastic deformation, the element is not changing the weight. It might become thinner or thicker, or the specific weight might change, but the overall weight is not modified. We substitute into here the linear interpolation of the deflections at node number 1 and node 2. And after integration, we just arrive at this expression here, which is the overall weight of the element in the actual configuration with the actual length, and just the arithmetic mean of the two vertical deflections at node 1 and node 2. Next, we have to determine the contribution to the virtual external work of the element. And again, we just apply the chain rule, just taking the derivative, the respective derivative here of the work, and post-multiply that with the variation of the free variable. You see here F popping up. That's simply simplification of the arithmetic mean of these two deflection components, which is nothing else than the deflection at the center of the element. We can replace the vertical deflection component by the difference of the actual vertical coordinate and the vertical coordinate in the reference configuration. So we do that for node 1 and for node 2. That are alternative notations. I already have mentioned that the specific property of the load case weight is that the weight is depending on the change of geometry. You see it again in this work expression. That's exactly the property of what we call a non-conservative problem in mechanics, which has no potential at the very end. As during the deformation, the path where the load is just changing its position, this load as itself is also changing values. If you go further to the variation, that means that with the variation, not the load itself has to be considered, but only the change of deflection, the F, or you see the deflection components, has to be varied. We have not to consider the variation of the length in this expression. If we go further in variation, as we again have to apply the chain rule with respect to the variation of our free variables, we have to concentrate this variation on this expression F, as what we see is just the center deflection as functions of the deflections at the nodes, or in other terms as functions of the vertical coordinates Z1 and Z2. Varying, taking the variation of F, in particular taking the derivative with respect to our free coordinates, which we may collect here element-wise. Again, in the vector here, these are the nodal coordinates for node 1 and node 2. And that means we can also collect the derivatives of F with respect to these three variables. Again, in a vector, which element-wise has 6 entries. So derivative with respect to x1, x2, z1, x2, y2, z2. And as our F, this abbreviation of the deflection, is only referring to the vertical coordinates z, the entries for x and y for the first and the second node are 0, of course. And taking the derivatives of F with respect to W1 is nothing else as taking derivative with respect to Z1, and W2 relates to Z2, which explains that we just have the entries 1/2 as the third component and component number 6. As F is a linear function, the second derivative of F is straightforward 0. Now we can just put everything together. So the contribution of the element with respect to the work, or negative the energy, is the inner energy and the external energy. The inner one just comes from our force density expression, as we have discussed before. And here that's the contribution of the self-weight in terms of the weight and the center deflection of this element. Again, taking variation, and in particular the specific or the special kind of variation for the weight term, we can just do that for every free variable, for each free variable in the element, where we have the 6 coordinates for the first node and for the second node. And we can collect these here, last not least, in what we call the residual force vector. For each coordinate, we take a derivative of L from this one, a derivative of F with that one, put it together with this, multiply it with QL or gamma L, and the result we just put here into this residual force vector. We can do that for each of the elements and just sum it up over the complete system. And that means at the very end, we have a residual force vector for the complete system. And the residuum has to be 0 at equilibrium. We have seen it already in the iteration history for the application of stiff. And that exactly is the basis of nonlinear analysis, that we take the residual force vector, that means in particular all components of that, which each of them are nonlinear functions in terms of the variables, and try to solve iteratively for each of these components of this vector to be 0. And we do that by applying the Taylor series expansion. That's exactly the Newton-Raphson technique. We have the residual force vector at step 1. We linearize this residual force vector by again taking the derivative with respect to the three variables. That will be receive the stiffness matrix and multiply that with the still unknown modification of geometry, which we can solve in this linear equation. And then we repeat that for every step which is necessary until we reach the goal where the residual force vector and all its components are 0. To solve for delta x, we take the residual force vector to the right hand side. Then it becomes negative. That explains this definition, that we take the negative residual force vector in iteration step n to be what we call the nonlinear load vector. Here we see it more in details. The negative residual force vector, respectively each of its component, are again here from the weight, contribution from the weight, and here the contribution from the energy through the force density. Again, taking derivatives of the residual force vector ends up in another derivative with respect to the three variables of the energy term and another derivative of the weight term now with respect to x. And there you see that we also, in this step of linearization, we also have to consider the derivative of the length. The derivative of the length only comes from linearization during iteration. It does not come from the variation of the constraint term. So that comes from the variation, that comes from the linearization, and there you see that is obviously non-symmetric in this dyadic product, as we call that, specific multiplication of these two vectors, the derivatives of the length and the derivative of this f function, which is nothing else as the center displacement of the element. As we now have determined the stiffness matrix and the load vector, we can solve for the change of geometry in iteration step n. It's simply the inverse of the stiffness matrix times the load vector, and with that we can just update the geometry for the next iteration step n+1 just by adding to the actual geometry in terms of the vector of three variables, just the change of these three variables, and we can just proceed to the next iteration step. Here we just collect the result if we just determine these expressions for all the 6 entries of the nonlinear load vector, and you just see it boils down to pretty simple expressions in terms of the force density and the difference in the coordinates in x and y direction, and for the z direction, again here the energy term from the energy term with the force density, and now here the weight term. And you see it's just half of the overall weight of the element, which just enters the force component number 3 and as well the force component of number 6. The stiffness matrix in iteration step n, again, is the derivative of the residual force vector components, as explained before. And you see the entries are pretty just condensed at the very end. On the main diagonal, you just observe the force density, as we just got that from the linear force density method. And of the off diagonals, we just have the negative force density. And we add in the third and in the sixth line, referring to the Z component, let's say, here the third one at the node 1 and the third one at node 2, which here in this vector is just here at position 6. You see here these extra contributions of the weight everywhere where the gamma just pops up. And quite obvious, this matrix is asymmetric, consequence of the non-conservative problem. If we get to snow, everything is equivalent to the self-weight with one important difference. And here we have to take the integral over the projection of the length into the xy plane. Again, assuming that snow is the weight of snow is just acting in the z direction. That means the definition of the snow load is that as with increasing slope of the element, there is less amount of snow. And that means we have to take, instead of the length, the shadow of the element into the horizontal direction, the xy plane. That is this one important difference. We consider the action of snow by the intensity of snow, and it performs work with the vertical deflection W as before. We just take the integral, do the variation, again considering that we have a non-conservative problem, and the function f again is the center deflection of the element, and we just can go further on again with this vector f and its derivative as before. And that's how in detail the nonlinear load vector or the negative residual force vector for the case of snow together with the force density action looks like. And you see it's in principle the same, just very similar to what we have seen for the weight. Here is the difference, the density of the snow and the respective projected length. And again, the snow only contributes to the third and to the sixth load component, actually these directions z in which the snow load is just acting. Taking again the derivative of the residual force vector, we just arrive at the second derivatives, which are the entries into the stiffness matrix, again the contributions of the force density, and here the contributions of snow. We just have to combine the derivative of the projected length that comes from linearization and the derivative which comes from the variation of this f function, the center vertical deflection of the element with respect to x. And again you see entries in the third and in the sixth line referring to the direction z1 and z2, which just appear at position 3 and 6 in this vector of free variables related to the element. And you see that the length has to be replaced by the projected length of the element, and the projected length, you see it, is simply the Pythagoras of the x difference and the y difference. The z difference is just missing. And we see also that this stiffness matrix for the element is asymmetric, and if we just add each contributions of the element matrices and vectors to the system residual force vector and the system stiffness matrix, we can just set up our system equations to solve the form finding problem. And here we have a first example. We have again this cable net here with two posts, and we add together here also the self-weight, and you see, or in this case, the combination of constraints of the length of these posts together with the self-weight contribution. Everything is nicely done. We just see in the iteration a quadratic convergence history. So just look here at the exponents. Now let's take a look, as we can just do this last example with stiff. You see from above our cable net. I have taken away the post, so the results will not be affected by extra constraints. And I have also taken away the load just by putting the load factor to 0. If we do the analysis, you see the method just converging after one step. That's exactly how it should be for the linear force density method. Let's now add the load. Just put the load factor to 1. Here it appears, and just to show you how we can type in the self-weight, let's edit the element, and you see we simply give in here a number for the specific weight. Okay, and let's do the analysis, and you see it's nicely converging after 3 iterations, indicating that the problem is now non-linear and converging with a quadratic rate of convergence. Let's now increase the load factor and continue analysis. Take away the reset data option. Let's go now increasing load factor to 2. And you see how the deflection is increasing. So again, the state of equilibrium now looks like that. Even more increasing the load. And we are now at this shape of equilibrium. I doubt that you really like it. That means to modify that, we have to increase the force densities, the pre-stress. And again, observe just the number of iterations, very fast, nonlinear, converging to our accuracy, which we just have given. Let's now modify this problem a little bit by indeed increasing the force densities. Let's go back and let's increase the force densities for the edge cables. I select all of them and take away the interior cables. Let's go to any of these elements and let's increase now the force density to 10, let's say. And let's repeat the analysis. A little bit better, but still the pre-stress inside the surface is not enough. Let's also increase the force densities of the interior cables. Let's take, instead of 1, or what should we take? 5? Wow, why not? And let's do again the analysis. Wow. Could still be better, should it? Great. Again, the interior elements. And let's also go to a force density of 10. Now it really looks better. Still, it appears now that we should increase the pre-stress by the edge cables so that we just receive a pleasing shape. I think you can imagine. Thanks. And last not least, we arrive at the final chapter of our presentation. It's about alternative parametrization of constraint problems. And in particular, we do that for the control of the position of nodes during form finding. That means we talk about constraints on prescribed coordinates. I recommend that you take a look at Hans-Jörg Schick's paper from 1974, which I briefly had shown you in the introduction, where I just also recommend things of what we do now in the following. When we deal with constraints, we already had observed, just refer to the chapter about length constraints, we had observed that Lagrange multipliers are equivalent to modifiers of the force density. And that's exactly the idea of an alternative parametrization, that we now directly modify the force densities instead of introducing Lagrange multipliers. There are certain consequences of doing that. Now the force densities are not fixed numbers anymore, they are variables. And constraints are introduced as what we call it now control equations. And we add those to the equilibrium equations. There come further consequences of this approach. We have now an extended system of equations, the equilibrium equations plus the control equations. That's equivalent to dealing with constraints as we did that before with the Lagrange function. The stiffness matrix now is extended by additional columns from the differentiation with respect to the force densities, because these are now variables. Here they are now variables. That means they have also to be considered when we do differentiation. There come also additional rows to the system matrix and to the right-hand side vector from the control equations. And as a consequence of handling those control equations, we have an asymmetric system matrix at the very end. When trying to understand how the reparametrization works, let's just take a look at the length constraints, which we have discussed in detail in the previous sections. Here it is, the Lagrange function, which just appears by adding to the energy term with the force density, the constraint term with the constraint here in the linear variant referred to the previous chapters, and multiplied by the respective Lagrange multiplier. Here's the alternative with the quadratic variant of the constraint, again with the Lagrange multiplier. If we now take the derivative of the Lagrange function with respect to the L, then we receive this expression, and there you identify the modifier of the force density as the ratio of the Lagrange multiplier by the actual length. And this modifier we will now call S sub q, the modifier of the force density. Here it is, S sub q, the modifier identified as lambda over L. If we do that for the quadratic variant of the constraint, again the derivative of the Lagrange function with respect to L, this modification looks like that. We will just identify the modifier as sub q directly as the Lagrange multiplier. We did that already in the previous chapter, just refer to that. Alternatively to what we see here, we can also write it like that. So another notation of the modifier, you see the modifier just appears to be introduced as the scaling factor of the initially given force density. And then this modifier is just identified to be the Lagrange multiplier over Q. This choice of reparametrization has a certain advantage. It simply means that we now can introduce the same scaling factor as sub Q for different elements and different force densities. So that means by this notation we can simultaneously scale all initially given force densities to reach our goal. That isn't so far better than this variant, because in this case we add something to the force density, and if you just imagine that we have the same modifier for several different elements with different force densities, then of course it has a different effect if you add the same value to different force densities of different scale. So here we prefer that one here, where this relative relation between the force densities remain fixed. We simply scale all of them with the same scaling factor. Then we just proceed as before. We have to go into the variation of the geometry with respect here for the three variables, just to receive the equilibrium equations. So this part of the variation of the Lagrange function, again applying the chain rule of differentiation, and this ends up into these contributions of each element. Just again go back to the previous chapters, and you see now that this notation here just differs what we have seen before, simply by this scaling of the initially given force density by this scaling factor. Why 1 plus the scaling factor? Simply because if we put SQ equal to 0, then we are back to the original formulation. That's simply a shift of the scaling factor with this effect that the initial case we receive by putting the scaling factor SQ to 0. Again, we have learned that this expression, which just arrives by the chain rule, is exactly the entry into the respective component of the residual force vector, which has to be 0 at equilibrium, as before. We now extend our system of equations, which now consists of the equilibrium equations equivalent with the components of the residual force vector, by the control equations, where we have as many control equations as we have scaling factors. Now, all of these functions are functions of the three variables, the coordinates, the three coordinates of our form finding problem, and the scaling factors. So the overall number of variables is now end of the number of free variables, the number of degrees of freedom, plus the number of control variables in control. And then now we can enter our standard Newton-Raphson iteration to solve for equilibrium, where we just have exactly the same situation, that now instead of the residual force vector we take the generalized one, we take the derivatives of the generalized one with respect to the generalized variables, and here the generalized residual force vector, where the negative of is the generalized nonlinear force vector. Then we can solve for the update of the generalized variables in step 1, again by multiplying the nonlinear generalized force vector by the inverse of the generalized stiffness matrix, and just arrive by iteration at the final solution. You recall that the generalized nonlinear load vector again is the negative generalized residual force vector, and the generalized stiffness matrix we just received from further linearization of the generalized residual force vector in iteration step n. And that's the vector of generalized variables, as I said, consisting of the original 3 variables and now the additional scaling factors of the force densities. And there we have already an example how we can apply that here for the example of the control of coordinates of nodes in our cable net. That is an example of a 2D suspension bridge. Here we have the suspension cable here, and the hangers. We have the deck with the self-weight. Again, we can simultaneously add our self-weight possibilities. And what we like to do is just to control here the x-coordinate should be -9. Here as well the x-coordinate. For this node we control simultaneously the x-coordinate and the vertical coordinate, just to clearly control the height of the suspension cable. Again, the horizontal coordinate. Here for the top of this post we control the horizontal coordinate, and of course we control the vertical coordinates of the deck just to receive horizontal deck. That's how it should be. And then you see, related to cables, the introduced scaling factors which we use. So we have from 1 to in total 9 conditions which we have to control, and for that we just introduce selected elements where we just define the respective 3 scaling factors. Additionally, we would also like to control here the length of the post, and that is the result. You see it nicely converges in 4 iterations with a quadratic convergence. That's how it should be, and we may check it here with respect to the coordinates system given if we just have reached the goal. Yes, we did. And nicely the deck is horizontal together with the self-weight which we just had considered. And the post, of course, has the proper length, which is supposed to be 6. That's how the generalized element load vector may look like. Again, we have the 6 entries with respect to the 3 variables, which are in principle given for an element with the 6 coordinates of the 2 nodes. And you see, for this example, we have just added 1 additional row for a control equation, where we just consider here as a further example as a control the vertical coordinate of node number 2 here, where we just prescribe the goal position by this value with the hat. That's how the vector of generalized coordinates look like. Now we have the 6 entries of the coordinates of the nodes, plus this extra entry for the scaling factor of the force density of this element. And that's how the generalized stiffness matrix look like for element. We have in the first 6 columns and rows the stiffness matrix as before for the linear force density method, with the difference that we now scale the force density by this scaling procedure as we just had introduced with the scaling factor as sub q. And of course we have additional rows here for every of the control function we just refer to this element. So again, for this example, where we just control the vertical coordinate of node number 2, you see the derivative of the control function with respect to the nodal coordinates. For this case, we just receive the entry 1 here for the derivative of this example function with respect to the only coordinate which just appears here, which is just set to that's it. And we have this extra column in the generalized stiffness matrix, which comes from the derivative of the energy term with respect to the scaling factor. Look at here. If you take the derivative with respect to SQ, just the Q remains, which has to be multiplied by the coordinate differences. Also note the bottom right submatrix, which is always filled with zeros, which is an indicator of a constraint problem. And that's another example where we can show more details. That's exactly the very first example where we have started with, referred to the first chapter. This 4-element cable net with the free node called C here at the center, with the three free variables XC, YC and ZC. Instead of having an external load here, we now would like to pre-stress this cable net and simultaneously control the position of the center node C. We introduce two conditions, C1 and C2, where we control the X coordinate by a given number and the Z coordinate by a given number. The Y coordinate quite obviously might be free. And we just assign to each of these two conditions element. That means the scaling factor of the force density of element number 3 should be introduced to control the first control equation, and the elements 1 and 2 are introduced to be related to the second control equation. That means it's exactly one of these cases that we just start with introduced force densities of element 1 and 2 and simultaneously scale them through the procedure. That means the relative relation between these force densities will remain. Then we have a set of 5 equations, the 3 equilibrium equations and the 2 additional conditions, the control equations. And that's how our vector of generalized vector of residual forces looks like, and at the solution they should be 0. That's more in detail how these equations look like. The 3 equilibrium equations and the 2 control equations, which should all of them be 0 at the form find shape in equilibrium. If you refer to the previous chapters, you will identify here our standard equation of equilibrium for the linear force density method, with the only difference that we now scale the force densities by the respective scaling factor. And we have to sum up again over all 4 elements, where all these entries here are referring to the individual elements. That's the vector of generalized variables with the 3 free coordinates of our center node and the 2 controls of the 2 scaling factors referring to the first and to the second control equation. So this number refers to the first control equation and that number refers to the second control equation. Then we can expand these equations, and if you look carefully you see the force densities of element 1 and element 2 are both of them scaled by SQ2, are relating to the second control equation, while the force density of element 3 is scaled by the scaling factor referring to the first control equation. And the fourth element we didn't use in this formulation, and therefore we don't scale it, and it just enters with this initial value. And again, comparing with the leading example of chapter 1, we will exactly identify the same structure of these equations, with the only difference having introduced the scaling factors. Then again, we can just create a table as before. For each of the elements 1 to 4, we just introduce these initial values of the force density and force densities. That's exactly what I choose here. You can choose any other numbers. And these are the numbers of the respective control equation. That means element 1 and 2 are referring to the second control equation, and element number 3 is referring to the first control equation, as indicated here, the first 2 elements, and here the element number 3. Then we introduce the initial coordinates of the 4 vertex nodes, here with some number, whatever that is, And then we just set up individual results or individual terms which appear to be necessary to solve the equation. So the multiplication of the initial basic force density with the coordinate differences of element 1, 2, and 3, and 4, and as well as the product of the respective basic force density with the y coordinate differences and the z coordinate differences. You see it here, here, and that means again summing up these columns and setting up the system of equations, and we'll be able to solve for the coordinates of number c. Then we have to introduce the prescribed coordinates here at node number c. That is, the x coordinate should be 0.5 and the z coordinate should be 1. And these are the two additional equations in our generalized set of equations, the 3 equilibrium equations and the 2 control equations. And since that is now a nonlinear problem, we have to iterate. So it's not as simple to solve for C. We have to do an iteration by Newton-Raphson and just receive at the optimal solution, which for the choice of the given data appears that x and z are of course identical to the prescribed values, and it just appears that the y coordinate should be 0. With this geometry having found after form finding, we can go back to determine the modified force densities by multiplying the basic force density by what you see in the bracket. I didn't give you here on this slide the final values of the SQs, but nevertheless that what we receive finally here are the multiplied force densities, and then we can solve for the forces taking the modified values of the force densities and multiplying that with the actual length of these elements. At this end, everything is as before. Straightforward. We can also set up a little Excel sheet to solve this specific problem. By the way, you see here's the result. The z coordinate should be 1 here, quite obviously. The x coordinate will be 0.5 at the optimal solution, and y is obviously 0. Here on this table, you see also the final values of the scaling factors, which are minus 0.8 for SQ2 and 0.3 for SQ1. That's substituting into this modification formulas for the force density. Then we just receive this final values 0.38 and 1.3 for the force densities of members 1 to 3, and member number 1 is not affected at all. Here we have the optimal values for node C, and with that information we can just set up the lengthes in the shape of equilibrium, from which at the very end we can just determine the forces by multiplying these lengthes with the optimal values of the force densities. Another example of a grid shell where we just found the optimal shape as an inverted hanging model with respect to the given load. And what we are doing here is that in addition of finding equilibrium shape, also to control the apex, the height of the apex at the highest node here, which is exactly that one in the ground view. And that's how it's modeled. You see here these relations, so that if we just select this node at the top, you see highlighted in green that all the elements are just related to this node. That means here we have an example that we have one control function controlling the z coordinate of this node, but simultaneously scaling all force densities of all the indicated highlighted elements. That means in this case all of the elements. And that is the trick, let's say, to keep the relative relations between those elements while we are doing the control form finding. That's the other way around. Just test this element, we see the force density of this element is related through scaling to the control function of this node. And you see here different examples for different choices of the coordinate -5, -3 and +3. In two cases here we find grid shards under compression, and in this case we have a cable net where the control is a positive number. And again you see, and that applies to all of these cases, that we have a nice iteration, very fast and even better than the second order of convergence. After a very long seminar, we just arrived at the summary. We have learned everything about the force density method. We call it an indirect approach to form finding because we apply force densities, which, as we have learned, are items of the reference geometry, which remain constant throughout the complete form finding procedure. There are consequences that we receive linear equations, which are most effective and efficient to be solved. The results which we receive are the deformed geometry and the true forces in equilibrium. And that is insofar the little drawback of the force density method, that we can only find compromises. It's difficult to have an idea when setting up force densities what could be the true forces. We have seen examples in that direction. In contrast, we call it the direct approach if we directly prescribing the true cable forces of the deformed configuration in equilibrium. The consequence is that we receive fully nonlinear equations, which eventually are even singular in kinematic. If we can solve them, the result is the deformed geometry. That special property of the equation system to be singular and kinematic, that indeed was an important motivation to invent the force density method as by Linkwitz and Schick. That also explains that large variety of alternative procedures and methods to solve these nonlinear problem of form finding. We have learned about the updated reference strategy as a further alternative to find solutions with prescribed cable forces, and in particular to find minimal path nets. We can say that constraints convert the force density method equations into nonlinear equations. That's the entry into what is called the nonlinear force density method, also already introduced and defined by the paper of Schick in 1974. If dealing with self-weight and snow load, we recognize that we have to deal with non-conservative mechanical problems. As a consequence, the stiffness matrices are asymmetric. And again, these kind of load cases convert the force density method equations into nonlinear ones. Last not least, we have introduced alternative parametrization, where we just take the scaling of the force densities instead of the Lagrange multipliers of constraints, and we have shown how that comes together with control equations. We've been looking at a special application to the node position control. As the very last example of this seminar, let's take a look at that one here. It's dedicated to the point of departure of our workshop, the Olympic roof. A little bit simplified, of course, not to make it too complex. So what are we dealing with? You see from the top view the cable net with the edge cables and the surface covering cables. We will see in a moment there are posts and suspension cables. What we like to control is the length of these posts, which will evolve just in a second, and we would like to control the z coordinate of this node. That's how it looks like, how we formulate it. So with respect to our coordinate system, we would like to have that the z coordinate of that node will be finally at the position -1, and it's the first control equation which we just have defined here. We are ready to start everything. Let's take a look at the algorithmic parameters. Everything is on default. We allow not more than 15 iterations. Perhaps you take a look here at the iteration steps and receive them. Let's go. You see it's nicely converging. with the quadratic rate of conversion to the final state. And we see it now, really, it's the Olympic Stadium or something which looks similar to that. Maximize it a little bit. You can walk around a bit and you see the important issues similar to the Olympic roof. We have here the edge cable, and now you see how the posts have evolved. And if you take a look at one of these posts, this one here, and there you see that we just have controlled the length of this post to be 8 again in terms of the dimensions we have chosen. And if you just again look at our control node here, that one, then you may see that these two elements have changed the color. And exactly these are the two, here we see it now highlighted in purple, that these are the two elements where we just refer the scaling of the force density. So these two elements have been adapted with respect to their force density just to arrive at the goal. And what is the goal? What was the goal? The goal was, let's go back to our control node, that one here. Let's take a look at the geometry and take a look here at the vertical coordinate. We have been starting with z equal to 0, and after deformation, yes, we have just arrived at the proper value, which is -1. In this example, many things just come together, which we just have learned in this seminar and is a specific subject of this workshop. Thank you for your patience to stay with us that long. And come back to the workshop layout. We have now finished seminar number 3 about the force density method, and the next seminar will be about some numerical aspects which have to be considered if we go into the nonlinear force density method.